So what we talked about and addressed yesterday was the idea of entropy, okay, which a lot of people refer to as the study of disorder. Okay, I prefer to look at it as motion. If you increase motion, you increase entropy. Okay, so I think that helps, at least as far as I'm concerned, wrap my brain around what's going on with it. When we're looking at increasing motion, we're looking at three possible ways to change that. You've got translation, rotation, and vibration. Okay? So we're looking at increasing the different possible motions. Okay? So that can be in an XY axis, that could be just a free rotation, or it could be even vibrational states. As far as defining it, it's kind of the representation of all of those energy terms. Okay? How does that represent or correlate to energy? Okay? So one of the things that you're going to be responsible for doing is calculating an actual number as far as the magnitude goes. And then we're also going to look at approximating. Okay? So kind of looking at the change. Does it go up? Does it go down? So one of the things I said as far as determining an exact number, at this stage in the game, what we'll stick with is a Hess's law type situation. Okay? We can look at the entropy of the products minus the entropy of the reactants to determine what the entropy is for that overall reaction. Okay? Some things to watch out for when you go through and do that is you have to have your balanced equation and make sure you include your coefficients, okay, when you put this together. I know this equation looks all messy and nasty, but it really isn't too bad. Remember, you just look up your entropy values, add them on the product side, and then subtract your reactant side from that. Okay? Oh, I forgot to look up an appendix. Shoot. So, like I said already, or yesterday, that appendix reference isn't necessarily true. While you guys are working on the quiz, I'll try and look that up and get an exact number for you so you know where to look for them. Okay? Questions about that? What? There's a quiz. So where we really ended yesterday was looking at, instead of looking at a calculation now, how can we look at magnitude differences? Okay? So what happens in the course of the reaction? Does the entropy go up? Does the entropy go down? So coming up with ways to quickly interpret whether it goes up or down without having to do calculations is a good tool to have handy, and it's something that's going to become increasingly important when trying to solve these problems. That way we can avoid having to bust out a calculator. We can just look at those negatives and positives, and maybe we can get an answer without having to plug in any numbers. Okay? So that's what we're going to start with today, and by start with, I mean now we're going to stop talking about it, and we'll go to the quiz. Nice little segue out of it. So when we're going through and trying to determine what's happening, a lot of what we're going to see in thermodynamics is kind of easier-ish because we're just looking and comparing things. We don't have to worry so much about the actual numbers. We're just ultimately comparing as we go through it. Yes?
It doesn't have nothing to do with that, but our scantrons, like, we have ones that are marked wrong, but that person is, like, right. And
Vice versa.
Yeah.
I don't know how that would work.
Did you erase something? And like,
Getting back to the topic of entropy, we said it's ultimately a probability, so increasing motion. So what we're going to try and do is come up with a couple possible rules to explain what happens. Okay, so if we looked at one of our easier examples, we looked at ice melting. Okay, what ended up happening to the possible locations? It increased because our liquid water is now going to shift and move around. So our motion has increased. So what we can end up looking at is that our entropy increases. So what would our change in entropy be for that reaction? Should it be positive or negative? Did our entropy increase or decrease? Increase, so what should the change in entropy be? Positive. Okay, one way to consider that, if I give you negative $5, did your bank balance go up or down? Okay, it would go down because I then take money away from you, right? Because it's a negative. So you have to be careful with how you look at these. When we look at ice melting, our entropy definitely goes up because we've increased the number of possible states, possible number of motions. If we look at the reverse, going from liquid to solid, what have we done to the possible motion? Decreased it, which means the sign should be negative. Okay? So that is only one case. So what we could do is look at a variety of other cases. So I think I borrowed this from the text. It looks like I made it. Doesn't look all that fancy. Looked up some entropy values for different states and evaluated what happens with the numbers. So if we take a look at our, in this case it's a slightly different one, a liquid to a gas in the case of water, what happens to our entropy? What happens to the possible motions? It increases. So if we go ahead and take a look at our value, what happened? It increases. Okay? So to calculate the change in entropy, we look at our final state minus our initial state. As we move from liquid to gas, what's our final state? Gas, 188, minus our initial state, 69. We still get that positive value. Okay? What happens if we look at the liquid to gas transition for a different element? Let's say bromine, or a different molecule. Liquid to gas, what would we expect? It should increase. Take a look at the numbers. It increases. We could look at a solid to gas, which is known as what type of transition? Okay, good job. Sublimation. As we move directly from a solid to a gas, what happens? Again, we're seeing an increase. Okay? This is something that correlates across all different materials. When we do a phase transition, as we go from solid to liquid to gas, we are increasing the entropy. Okay, so this can give us, sorry, I gave a little step in. If we're looking at solids, we could go back to the molecular level. If we look at solid ice versus liquid ice, I know you got that black background issue. Solid ice is much more organized. You notice each of those individual molecules is frozen in a particular spot to generate the geometric lattice. When we move to liquid water, we don't see that repeating pattern. Okay, why not? Because there's more motion associated with each of those water molecules. They flip and change their interactions. That increased motion reduces the order of our overall system. This is where disorder comes from as far as deciding what entropy is. So a lot of people refer to a measure of the disorder of a system. Okay, and that's because we can see it a little bit easier when we look at solids versus liquids, versus gases for that matter. Okay? And we could look at solid iodine to gaseous iodine, just because I happen to have another picture of this. Take a look at the solid. It's relatively condensed in that nice little spot at the bottom. As soon as we make it a gas, what happens to it? And now it floats off everywhere. Okay? So we've increased the possible motions. We've disorganized where those atoms are located. Okay? So our first rule when it comes to determining entropy is going to be looking at phase changes. As a phase transitions from solid to liquid to gas, we get an increase in entropy. Okay? Why start with this rule? Why not start with any of the other rules? Granted, you may not know what the other rules are, but why should we start with this one? It's the easiest to wrap our heads around. Okay? Not only that, it's also going to generate the biggest difference in entropy because we're moving from a solid phase to a liquid to a gas. Okay? We're seeing a dramatic increase in the entropy. Okay? So when we go through each of these rules, we need to apply them step by step. So just like we did with our acids and bases. We looked for charge, we looked for atom effects, then we started to look to those other rules. Okay? Increasing the number of electronegativity or electronegative elements around it. Increasing the number of oxygens around it. Okay? Same idea is now going to apply with entropy. We're going to start with every single problem looking at the phase transition first. Okay? If that phase transition is favorable, we can say there's our transition. What if we don't have a way to look at it? Okay? For instance, if we go through with a quarter, okay, if we flipped a quarter, what would you call? Okay, everybody said tails, but let's say it came up heads. Okay, what we're looking at is ultimately an odds there. Okay, what's the probability of getting either one of those choices? It's 50-50. There's no difference. Okay, what happens if we now take two quarters? what should you call? And we assume no order in this. Heads, tails. Why do you pick heads, tails and not say tails, tails, or heads, heads?
Higher probability.
There's a higher probability of hitting the heads, tails because there's more possible ways to get that. Okay? We aren't looking at any phase transitions there, but what we're looking at is probabilities. Okay? Probabilities are not the most fun to work with, but entropy is kind of a game along those lines. Okay? So according to our best call, we would call heads, tails. Why? Because we get two possible ways that that could outcome. Okay? So we can look at the number of possible states, if we will, when we're looking for entropy. Okay? So if we don't have a phase change, we can now look at ultimately the numbers. So we just compare across a reaction. Which one has more things associated with it? The more things there is going to increase the entropy because there's more things to shift around and move. Okay? So best probability would generate highest or lowest entropy? Okay. Lowest entropy would be saying pick something like the heads-heads transition. Okay. Is that the favorable transition? Is it going to favor the best odds? We want our highest entropy. We want the highest probability state. Okay? I know it's kind of odd, so, did I not give an example? Yes, I did. Good. Okay, so our rule number 2 is going to look at picking the side of our reaction or the situation where we generate the most probable outcomes. Okay? So when we look at individual reactions, okay, we could look at a couple different examples. You'll notice that the wording, I think, changed on this from what the slide says. Nope, looks like it's the same. Okay, good, I fixed it already. We could look at a couple non-chemistry examples, and we can look at some chemistry examples. Okay? This would be a good format for something you could see on an exam. Which of the following decrease in entropy? You would then have to go through and decide for each of those reactions, did it increase, did it decrease? Okay, and evaluate. Okay? So if we look at kind of the following situations, those are a little bit trickier to work with. If we flip 4 quarters, which is the more likely or probable outcome? 2 heads and 2 tails, which has the highest entropy? 2 heads and 2 tails. Okay? Because it's the highest probability of getting that. Okay? If we go through and look at poker, getting 2 pair or a royal flush. 2 pair is a higher probability than getting a royal flush. So which one has the higher entropy? The 2 pair. Okay? What happens when we look at some balanced reactions? That's ultimately what we have to deal with, is some chemistry involved in these. Okay? Which of the following situations shows a decrease in entropy? So if we take a look at that first one, our very first rule says to look at phases. So let's look across that reaction. What happens to the phase? It stays the same. So rule 1 fails. So now we can move to rule 2. We're looking at favoring based on numbers. Okay, so as we run through this reaction, we move from 3 moles of a gas. I don't care what gas they are at this stage. I just have 3 of them, moving to 2 moles. What happened to the number of possible positions? It decreased. So what would the sign on our entropy be? Negative. Okay? Kind of makes sense? Okay? Go through and try the other 3 on your own. If you've got questions about it, raise your hand. I'll come around and help you out, because I think I've got the answers on here. It's also easy to screw up. What happened in the second situation? We go from 2 to 1. It's a decrease. How about in the, I guess that's the third situation? 1 to 2. Increase. Last situation? That one's kind of tricky. What's going on with that last one? I see 2 to 3, which would say increase. Is it an increase?
Increased by gas.
Oh, shoot. It was supposed to have swapped the other direction. It didn't swap the other way. What number should we actually be carrying or looking at? Is it 2 to 3? No, it's 1 to 2. Why do we only evaluate the 1 to 2? We only look at the gas. Why do we only look at the gas? There it is. The gas has the highest entropy. So if we're going to compare across this reaction, I don't care about the entropy of those solids because they aren't going to contribute enough to the overall entropy of that side of the reaction. Okay, so I can cross them out of my analysis. And what we'd be looking at is still an increase because we're moving from 1 mole of gas to 2 moles of gas. Okay? That was supposed to be a trick question where it went the other way. Okay? So realize I could go through and build an equation where if you just add up the reactants numbers and the product numbers, it could look like an increase. But then if you go back through and evaluate the phases, it might actually be a decrease. Does that make sense? I'll have to hit you with an example on that tomorrow, okay, because I cannot think of that off the top of my head. Okay? So make sure when you evaluate, you're looking at your rules appropriately. Stick with your phases first. So when we look at that last one, our first rule is to look at our phases. We would eliminate the solids because the gases have a higher entropy. Now we can move to rule number 2 and evaluate between them. Okay, and we can look at the numbers. Make sense? Okay. How many people think this is easy? So far, not too bad. One of the problems that you'll find with thermodynamics is that a lot of these comparisons are seemingly easy. And as easy as they may be to get, they're also really easy to get wrong. Okay? So you have to be super careful when you go through and answer these questions to make sure that you aren't making a simple error, like ignoring phase transitions. Okay? So be very careful and methodical as you approach each of these. Okay? Next issue. When we look at this reaction, we're taking hydrogen gas plus iodine gas and going to 2 moles of hydrogen iodide gas. We apply our first rule, phases. Do we have any phase issues to worry about? No. How about our second rule, the numbers? It's 2 and 2. Okay? So at this stage in the game, we started with rule number 1, giving us our biggest entropy difference. Then we moved to numbers, giving us a slightly smaller entropy difference. And now we're moving to a situation where maybe our change in entropy is very, very small, but is it something that we can actually calculate and figure out the sign on? Okay? And this is where we're going to look now at complexity. If we compare these across the reaction, what we're going to do is try and determine what possible states are there for each of these things. Okay? So why is complexity part of this? Let's take a look at a mole of hydrogen gas or a mole of iodide gas. Okay? It's a diatomic molecule, right? So if we look at a nice little picture of it, we'll go ahead and call this hydrogen just because hydrogen looks blue, right? Close enough, right? Maybe? Okay, never mind. If we take a look at that diatomic molecule, and now let's rotate it 180 degrees. Can you tell I rotated it? No, I did actually. I went into PowerPoint and I did the rotation of 180 degrees and still can't tell a difference. So for that individual molecule of hydrogen gas, I don't see a rotation of 180 degrees as a new possible state because it looks exactly the same as the initial one. What happens when we move to a molecule of HI? Now when we pick that molecule up and rotate it 180 degrees, can you see the difference now? Yes. Which means we have increased the number of possible states. HI has more possible ways that it can be oriented in space that is unique from one of the other positions. Okay? And what this is getting into is kind of a complexity. The more complex the molecule, the more entropic it is. The higher entropy it's going to have because there's more possible ways that you can spin, flip, or rotate that molecule in space. Okay? This rule ends up being a lot more narrow. We're seeing very, very small differences in entropy potentially within these, but you should still be able to pick that up. Okay? So our rule 3, the more complex the molecule, the higher the entropy. Okay? So let's take a look at some examples that we could run through. Most of these are a bit dicey for you guys to deal with because you have to have a little bit of understanding of Lewis structures. So I'll go through and draw some Lewis structures for some of the harder ones, I think. But we should be able to do B right now. Okay? If we go through, no, we pretty much need Lewis structures for all of these. Okay, you take a look at B. What do you think? Which one's more complex? Okay, we might say CH4. Why? We got more hydrogens. But let's take a look at Lewis structures on this. Ooh. If we take a look at the Lewis structure for ammonia, okay, if you guys remember this from 151, we get this overall shape where the wedge means our hydrogen's coming out at you. The dash means that hydrogen is going away. We've got the shape known as its class, its electron geometry would be what's it? Tetrahedral. If we go into the bond geometry, got the right idea on trigonal, but it's not planar. If it was planar, we could just draw it flat. We wouldn't see any wedges and dashes. It's a pyramid, trigonal pyramidal. Okay. What happens when we move to methane? It's tetrahedral. Okay? Why is this different? If we pick up, spin, flip, or rotate, say, the methane versus our ammonia or the NH3, what happens? We can potentially rotate the ammonia into a position where that electron pair appears to be in a different spot, which means it's going to have more possible states, which means higher entropy. Someone needs to remind me at the end of class that I need to do that. Please. Okay. So that was our structure for ammonia and methane. Okay, realize that that is a more difficult one. You actually have to have the structure handy to evaluate these. Okay, which means with the rest of these, I'm pretty sure with the, come on, erase. With the rest of these, it's going to help to actually have structures drawn out for them. So let's go ahead and take a look at some structures. We have C2H4. Sorry, let me try that again. Oh. It's not showing up very well either. Let me get you a better color. Red always makes people panic, so let's stick with red. So there's our C2H4 versus the C2H6. And this tedium of drawing in all the hydrogens is one of the reasons why organic is great, because we just pretend they're there, so we don't have to draw them all on. So what do you think about the C2H4 versus C3H6? Well, I already forgot it was. C2H6. Which one would be expected to have the higher entropy in A? This one's also tricky. This is where structure comes into play. Seeing some pointing to C2H4. Does everybody agree? Why do you say that one's more complex? Can the double bond turn? It can't turn, but the single bond in C2H6 can turn. So we can potentially change the alignment of the hydrogens with respect to each other in the C2H6. We cannot do that in C2H4. What does that mean about possible states? C2H6 has more possible orientations, more possible states, which means higher entropy. What happens when we move to C? Cu2 or copper, what was that, copper 1 oxide? It's probably going to have more entropy because copper 1 oxide is the one on the right, by the way. Why do we call it copper 1? What's the 1 stand for? The oxidation state of that element. So we have copper 2 oxide on the left, copper 1 oxide on the right. Why is copper 1 oxide on the right more entropic?
It's that double bond.
Okay, we don't have that double bond in that state. We can spin, flip, and rotate that a little bit more. Okay, we can get more possible states with the formula. Here, let me just box that, because that whole copper 1, copper 2, I'm sure is confusing people. We get more possible rotations for that molecule than we do for the other. What happens with the last one? C6H6 is a ring structure. I know it's a bit messy there. Okay, what can we do with that ring structure? So imagine putting your hands together in a ring. Okay, can you rotate around one of those bonds entirely? Nope, what happens? You break the ring. If we no longer have the ring, can we rotate around it? Any one of those bonds? Yes. Increased rotation means higher entropy. Okay? So when we get into this rule of complexity, it's not as easy to evaluate. You have to know a little bit more about the structures and a little bit more about what's happening in each of these states. Okay? Along those lines, to go through and ask any one of these questions, what did I have to do? I had to draw them all out for you so that you could see them and evaluate them, which means it's a more difficult question for me to write. Odds are, probably won't see a lot of them on the exam. Okay?
So which one is the one for D then?
Okay? Questions about that? Other rules. So we'll cover one more rule when it comes to entropy. Okay, again, our first two rules were our largest differences in entropy. A lot easier to see. We're looking at phase changes and we're looking at numbers. Okay, it makes things relatively easy to jump at answers. As soon as we start getting more and more refined and start comparing things where we're looking at complexity of structures, that gets a bit dicey to evaluate because we have to look at actual structures. We can take it even further and look at another example. What happens if we take some purple food coloring and dump it into a swimming pool? Okay. The reason I came up with this example is actually back in my high school. The senior class decided it would be a fun joke to dye the swimming pool purple. So they stole some potassium permanganate from the lab room, dumped it into the pool. Anybody know the problem with that? Pools are chlorinated. You add potassium permanganate into it. You generate, first off, a nasty brown sludge of a manganese oxide precipitate and chlorine gas, their prank didn't turn over so well. So don't add permanganate to a swimming pool. It's usually a bad idea. Instead, what you could do is add purple food coloring, okay? Or maybe throw in a candy bar. That's kind of entertaining too. Just a chocolate one. So back to the example, purple food coloring. What happens when you add it to the pool? Does it stay concentrated in one spot, or do we eventually see it spread out through the whole thing? It spreads out. Okay, why? If we look at phase transitions, do we have a phase transition? Nope. How about numbers? Nope. Complexity? Nope. So we've kind of run out of ways to explain why that food coloring would disperse through that whole process or throughout the whole swimming pool. And that's where we end up back with yet another rule. We are increasing the possible number of states, okay, by having these two solutions mix. Okay, so what ends up happening? Barring any other rules. So remember, we're going through these in priority. Okay, the entropy of the mixture is greater than the individual entropies. Okay, this example is even more difficult to select, and I'm pretty sure predict, or to come up with examples of. So much more difficult that I didn't even come up with any examples beyond adding food coloring to it. Okay, your textbook, I think, comes up with another option. What happens if we take sodium chloride and add it to water? What's our very first step? Not the very first step. It starts as the solid, and then it goes to being sodium chloride aqueous. Then once it's aqueous, then it dissociates. Okay? Even that's a bit of an odd one, because if we take a look at that as an example, we took a look at sodium chloride aqueous going into sodium ion and chloride ion. Sure, we could go through and say that our products are a higher entropic state because we're looking at this. What are we looking at? Our product mixture is greater than the individual, where we haven't separated it. Okay, so yeah, that's true. But was there an easier rule to look at? Rule number 1, phase transitions. Do we have a phase transition? It's aqueous, and I know I didn't show those, and aqueous. Is there a phase transition? No. Rule number 2, numbers. How many molecules do we have on the left? 1. How many molecules do we have on the right? 2. We don't have to go all the way to looking at it dissolving to see that difference in entropy. We can look at it purely based all the way back to our numbers, our rule number 2. Okay? So this rule number 4 is one that we'll mention just because it covers pretty much the swimming pool example, so it's kind of important in that respect, so we can tie it back to things we've already seen. But it's not one that I could really ask many questions about. Okay? So when we go through and take a look at entropy relationships, what you'll be asked to do is compare things. Compare one species to another and say what happens to the entropy. Did it increase? Did it decrease? Which one has a higher entropy state? Okay? The other option is you can be given a reaction and say what happened in the course of this reaction. Did the entropy go up? Did the entropy go down? Okay? When we're looking at a reaction, which way does it go? Left to right, right to left? It's always left to right. Okay? When we're looking at our thermodynamics, we don't care as much about equilibrium. We're always assuming our transition is happening left to right, just like we did when we calculate the entropy for the reaction. Okay, we'll bring in equilibrium in a little bit, but it plays a much smaller role. Okay, questions about those rules? Okay. Let's see how well you guys can do with it. So here's some examples. Go ahead and work on them. If you've got some questions, raise your hand. I'll come around and help you out. And I will very quickly draw on. Okay, so let's crank through these, assuming that I did this right. We look at that first equation. We actually already talked about this one. Which one has the higher entropy? Reactant or product? Product, which means the change in entropy should be positive. And we just went through our higher lower explanations. So graphite versus diamond, it's a little bit trickier. Okay, which one's more organized? Diamond, hence we've got a harder structure. Okay, that crystal lattice is set up so that it's very, very rigid, which means less possible states for our individual diamond atoms. Less possible states means lower, so we're looking at a negative value. When we move to the next one, it says 2 to 1, which would suggest negative. Is it 2 to 1?
No.
No, what is it?
1 gas, 0.
1 to 0. So it's still negative. Man, why didn't I pick a tricky one? 1 to 0, we're still getting a negative. Okay? Where's our relationship? We apply phases first on that one, then we applied our numbers. Last one. Or sorry, not the last one. Bromine versus iodine. First rule is what? Okay, our first rule is phases. We don't have any phases. What's our second rule? Moles. Do we have a difference in moles or a difference in numbers? No. Third rule. Complexity. Complexity is a difficult one, and that's the one we're going to have to kind of look at to evaluate this one. Okay? What's the difference between those two molecules? They're both diatomic, 2 atoms, so we would say no difference. We could try and move further on down the rules, but we haven't hit a rule. Okay? What else is the difference between bromine and iodine? Where they are on the periodic table, which ultimately comes back to size. What's the difference when we're looking at the size? Number of our electrons. Which one's more complex? One with less electrons or one with more? One with more electrons. The higher entropic state we would apply to iodine. Okay? Have I been doing these right for those of you that have the answers? Okay, that's good. The very last one. I know it's a bit messy down there. What we'd be looking at, shorthand, this structure versus this structure. Same number of carbons, same number of hydrogens. Which one of those is a higher entropy? Okay. Go through and use your hands. Envision with the cyclopropane, can we move any one of those bonds? What happens if I rotate around my thumb? Do I have cyclopropane anymore? Nope. Okay, so I can't do that rotation. It's prevented. If we go to our propylene, okay, now it's a straight chain. Can I rotate about my thumb? Is it still my right hand? Yeah, it is my right hand, isn't it? Yeah. It's still the same structure. So we can do different orientations and rotations within the propylene that we can't do in the cyclopropane, which means which one has more possible states? Propylene. Which one has the higher entropy? Propylene. Okay, or lower it the other way. Make sense? Comfortable with that? Lots of examples this time around. So, I think this is actually going to work out pretty well. So we can kind of get back to the point. We did a kind of a detour off into what made up entropy. So we'll go back to what we were trying to do. We were trying to evaluate an overarching summary that explained all energies when we looked at our individual reactions. So we've expressed 3 things that contribute to our inherent energy for an individual position, be it reactants or products. We looked at enthalpy, the energy found within individual bonds. We looked at temperature. The more energy we added as the environment changed how our molecule could move. And then we also evaluated what that motion would do, ultimately our entropy. So we now have to somehow combine all of these things into an overarching theory. What? Dang it. Okay. Oh no, this goes back to it. This does work. So if we take a look at entropy, what we're trying to do is again come up with relationships between these. The enthalpy didn't matter what temperature it was. That's the energy stored in that bond, period. Okay? If we looked at temperature, when we change the temperature, what happens to our motion? also changes. If it's changing, that means our motion and our temperature must somehow be linked to each other. Okay? So when we're looking at how those two contribute, they're probably going to be contributing in a similar term or grouped to each other, independent of our enthalpy. Okay? So if we go through and take a look at a little bit more with our entropy, what are our units on our energy? Joules. Okay, so if we look at our entropy value, it's going to have to somehow have joules involved in it because it has to contribute to our energy. Okay? If we take a look at our enthalpy, what are the units on our enthalpy? Joules per mole, but we could say the same thing per mole with our energy, our inherent energy. So we can run with just joules. Okay? When we move to entropy, we have to come up with some way to tie temperature back to our energy value. Okay? And we said they were directly related, so what we're going to do is play around with this. Our reaction can still proceed if our enthalpy equals 0. Okay? So we have 0 energy term, which means our entropy somehow has to incorporate a joule unit as well as a temperature unit so that we can account for those two things. To go through and do that, what we end up determining or discovering is that our temperature times our entropy makes the most sense. Okay? Next big issue to look at would be units on our entropy. And we did a plus minus between our enthalpy and our temperature entropy value because we don't know whether to add them or subtract them at this point. We do not multiply because if we multiply, those two terms would then be inextricably linked. Okay, the only way we can separate them from our overall equation is to do a plus minus. Okay, for instance, we know a reaction will proceed even if the enthalpy is 0. If I multiplied everything together, what happens? Everything becomes 0. I don't have the reaction proceeding anymore. Okay? So what we want is to keep those two terms as separate as possible. The easiest way to do that is with that plus-minus system. They have to be somehow adding to each other. The next issue is trying to push through with our units, deciding for units on temperature. What units should we pick? Okay, Kelvin. I didn't even include Fahrenheit in this. Why would we choose Kelvin and not degrees Celsius? Kelvin's an SI unit, but why do we even care about that? If we look at Celsius, what happens? It goes negative. If we're looking at mathematics, how often do we want to deal with these pluses and minuses shifting all over the place? Okay? We want to avoid that issue as much as possible. So we end up using Kelvin because it's an absolute temperature scale. We don't have to worry about the negative value, which is actually kind of a lie. They just discovered negative temperatures. Okay? Negative kelvins, that is. So we're looking at Kelvin as a unit. Okay? So now we can try and propagate this a little bit further out. What unit should we expect on our entropy? Well, we went through and said the units on our inherent energy needed to be joules. Our enthalpy needed to be joules. We know our temperature is Kelvin. Somehow or another, if I'm going to add these two terms up, the units at the end of this calculation, temperature times entropy, needs to be joules. It has to be the same as our enthalpy. So what does that mean? You can do some unit elimination, and we can end up with joules per Kelvin. Okay? You can almost always see that mole value show up or not show up depending on what you're solving for. Okay? The plus minus, I'm going to talk about it just a little bit more to try and look at the plus minus. We'll come back to this. Deciding whether it's plus or minus goes back to what we would expect to predict for a reaction occurring. Okay? The easiest thing to evaluate would be our enthalpy. Our theory said our enthalpy needed to be negative, and it predicted most reactions. If our enthalpy was negative, our reaction occurred, which would mean what would be the sign on our inherent energy? Also negative. Okay? So the idea is to now go through and take those manipulations and say, okay, if I need a negative value, what do I have to do with all the other signs to add them up to suggest that we would get that reaction to go forwards? Okay? The bottom line on this I don't really remember all of it. We'll jump to the end. Nope, too far. Our plus minus should be negative. We'll walk through that process tomorrow. Okay, so our relationship is that our inherent energy is equal to our enthalpy minus the temperature times our entropy.